Hello friends, welcome to the next section of thermodynamics of polymeric systems under the aegis of polymer process engineering. Now in previously we covered what is thermodynamics, how this thermodynamics is applicable to the polymeric system. We discussed about the polymer PVT data, we discussed about the equations of state for the polymeric system and calorimetric data. Now in this particular segment we are going to discuss about the enthalpy and entropy calculation for polymers. Then we will discuss about the phase behavior of a polymeric system. We will discuss about the fugacity and activity. We will have a brief outlook about the equilibrium conditions because it plays a very vital role during the polymerization process. And then I will discuss couple of theories which are applicable in the polymeric thermodynamic studies. So let us start with the thermodynamic properties for polymers. The principal thermodynamic properties used in processing, they are enthalpy and entropy. As per the previous discussion, when we are having the granules and we need to develop any kind of a useful product, and ultimately we need to melt or we need to subject in those melt in either in the different type of a molding operation, where we need to apply the heat, and this heat plays a very vital role in shaping all those polymers that becomes the useful product over the period of time. Now, the knowledge about those thermodynamic behavior is quite essential, and these are usually represented in the form of enthalpy and entropy. But you cannot measure these enthalpy and entropy directly, therefore you require certain correlations, and as discussed in the previous lecture that these correlations can be developed with the help of a pressure, volume, temperature data. So therefore, the importance of these pressure, volume, temperature data cannot be overlooked. So these enthalpy, as evident when we are saying that enthalpy and entropy, they are dependent on the pressure, volume, temperature data. This can be calculated from the appropriate calorimetric data and PVT data. Another factor this must be considered in is the state of polymer, that is solid or molten. If it is molten, then again you need to have such kind of a data for your ready reference. Now for solid polymers, the enthalpy can be written as the temperature and pressure constant minus, that is T start to T Cp solid dt. This is a usual thermodynamic equation. And for entropy, it can be represented as STP minus this T star is the base temperature over T dt. Here H is the enthalpy, S is the entropy, T is the temperature, we can say in the absolute, P is the pressure, either you may represent in psi or atom, atmospheric. Then Cp is the specific heat at constant pressure, usually represented by the calorie per gram Kelvin or BTU per pound degree Rankine. T star is the base temperature. This equation represents the change in the enthalpy and entropy at constant pressure, because you see here we have kept the temperature, pressure constant from the base temperature at any particular temperature. Now, in the calculation of these properties, the constant pressure is taken as atmospheric, since you see that Cp data, these are available at that pressure, and the base temperature, that is T star, can be any number of different points like 0 degree Celsius Kelvin or 100 degree Celsius, as per them. That is, sometimes it is referred as the reference data. Now it is set to some extent by the availability of Cp data. So the benchmarking is either this reference temperature or T star or the Cp data. Now for example, like base temperature T star lower than degree Celsius should not be chosen if specific heat data are not available below that particular temperature. The end result of computing enthalpies and entropies to yield data dependent on base temperature selected. Whatever base temperature you have selected, that depends on over it. Now, however, it is quite important to notice that most computations involving the enthalpy and entropy actually involve change in these quantities. Like suppose we want to determine the enthalpy change from a temperature T1 and to another high temperature T2, then delta H, if we move from T1 to T2, this can be given as H T2, pressure we are keeping constant, then this is the base temperature or reference temperature minus H T1, here we use T2 at constant pressure, H base temperature, and delta H from T1 to T2, this can be given as H T2P minus H T1 at constant pressure. Hence, the change in the enthalpy or entropy at constant pressure with temperature is independent of the selected base temperature, that is T star. So, the method frequently used to compute an enthalpy change is to solve the CPdT integral graphically, and this is schematically shown in this particular figure. This figure shows the change of enthalpy with temperature. So, x-axis temperature and y-axis the enthalpy. Now, this particular area ABCD, this represents the enthalpy change. So, the same approach can be used for entropy by plotting Cp over T versus T and then evaluating the area under curve. Now, semi-crystalline and amorphous polymer undergo somewhat different experiences as the temperature increases. So, the semi-crystalline polymers ultimately exhibit a melting point and form a true melt, whereas the amorphous usually soften but do not melt. Hence, the solid polymer equation for enthalpy and entropy, they are valid for high temperature. On the other hand, the discontinuity, that is the melting for the same semi-crystalline polymer, makes it necessary to change the form of the equation for these materials. So, the altered form of semi-crystalline polymer, this can be given as H at constant temperature and pressure, that is for the melt, minus H at the base temperature and pressure. This can be represented as from base temperature to the temperature of fusion. Cp we need to have for the solid, dt plus delta H fusion plus from T fusion to T Cp melt dt. And for the entropy, this can be given as S at constant temperature for the melt minus S for the base temperature and constant pressure from base temperature to fusion, then Cp for solid over T dt plus delta H for the fusion over T fusion plus integration from T fusion to T Cp melt over T dt. Now, the specific heats for the molten and solid cases, they are different in both the equation. The heat of fusion of the material must be included in that particular aspect. Basically, these equations involve at constant pressure taking material up to the melting point, that is the temperature of fusion, and melting it, that is called the heat of fusion, and then moving from melting point up to the final temperature. Now, once again, as with the solid material, the choice of base temperature becomes unimportant. since the usual case involved determining the change in the enthalpy or entropy, and that is a change in enthalpy of a melt from at one temperature to another. This can be given as delta H melt, and let us take from T1 to T2 for both the cases. Then it can be given as H T2P for the melt minus H at constant base temperature and pressure minus H at constant T1 and constant temperature, constant pressure, then HT base temperature and P, and delta H melt from T1 to T2. This can be given as H T2P melt H T1P melt. Now, there can also be a pressure effect on either enthalpy or entropy. Such effect can be given as HTP minus HT base pressure from base pressure to P, V minus T del V over del T at P dP, and STP minus ST base pressure is equal to minus base pressure to P del V over del T dP. Now, these equations are constant temperature, and this base pressure represents the standard pressure, usually the atmospheric pressure. So, 1 atmosphere is chosen for this kind of a thing and generic equation. The base is usually taken for pressure and temperature that are atmospheric pressure and either 0 or 25 degrees Celsius or 273 Kelvin or 298 Kelvin. The pressure corrections can be applied for either a solid or molten polymer. This is the only stipulation that the function del V over del T at constant pressure be determined in the appropriate state, and that is the solid or melt. Now, let us talk about the phase behavior of polymeric solution. Now, formation of solution is quite important, sometimes with the help of a solvent and sometimes with the help of his CO things. The equilibrium condition for phase equilibrium can be derived in the simplest way using the Gibbs energy. We have talked about this Gibbs energy in the previous segment. Now, according to the second law of thermodynamics, the total Gibbs energy of the closed system at constant temperature and pressure is the minimum of equilibrium. Now, if this condition is combined with the condition that the total number of moles of component I is constant in a closed system, where you see that can be mathematically, you can represent like this, which is constant. Now, mu I alpha is equal to mu I beta and mu I pi. Now, I is 1, 2 up to n. Now, this particular n I alpha is the number of moles of component in ith phase A, and the equilibrium condition given by the second, this equation can easily be derived with the system for pi phases. These are the phases. Now, let us talk about the chemical potential in brief. The chemical potential of a component I in the phase alpha is defined by the equation which we are going to write, that is mu I alpha is equal to del Ni over alpha at constant pressure, temperature, and Nj is not equal to I. Now, let us talk about the fugacity and activity. Now, in thermodynamic treatment of phase equilibria, auxiliary thermodynamic functions such as fugacity coefficient and activity coefficients, they are often used. These functions are closely related to the Gibbs free energy. Now, the fugacity of a component I in a mixture if we are representing by Fi, is defined as phi I. This is the fugacity coefficient is equal to fugacity of the ith component, and this is the Pi. Now, according to this definition, Fi is equal to the partial pressure of Pi in the case of ideal gas. So, the units of fugacity is same as the pressure. Now, it is the measure of the deviation from ideal gas behavior or ideal behavior. So, we have already defined the fugacity coefficient in the previous slide. Now, the fugacity coefficient can be calculated from any equation of state. Let us take about this RT is equal to ln phi I is equal to 0 to p integration Vi minus RT over P. All these terms are in their usual denotation, and RT ln phi I is equal to minus infinity to V, the integration del P over del Ni V at constant temperature, volume, and Nj is not equal to I minus RT over V plus RT ln summation I Ni RT over PV. Now, sometimes activity plays a very vital role. This is defined as the ratio of Fi and to the fugacity of component I in the standard state, that is denoted as Fi naught under the same pressure and temperature conditions. So, Ai, that is the activity, is defined as Fi bar at P same temperature, pressure, and X over F naught I under the same temperature, pressure conditions under the standard condition. So, the ideal solution is defined as Ai, this is ID represents the ideal, is equal to Xi. Now, the activity coefficient of component I is a measure of deviation from the ideal solution behavior, so that the fugacity of non-ideal liquid solution, this can be written as gamma I is equal to Ai over Ai ideal, and the fugacity of ith component can be represented as Xi, that these are the mole fractions I F naught. Now, the activity coefficient can be calculated from a model for a molar excess Gibbs energy, sometimes referred as GE. Now, this can be mathematically represented as RT ln gamma I is equal to del summation of Ni GE over I and del Ni at constant pressure, temperature, and Nj is not equal to I. Now, in this approach, the standard state fugacity Fi naught of a liquid component is usually the fugacity of the pure liquid component and is closely related to the vapor pressure of ith component under the saturation condition for that particular segment. Now, on the vapor pressure curve of a pure component, we can have this like Fith component in the liquid phase, P saturation T, these are the constant, then Fiv, the Pi saturation T, that is equal to, this is for the vapor, phi I V Pi T in Pi saturation. Now, another, that's Fi for the liquid given at the desired pressure and temperature. This can be represented like this: Pi saturation, then e to the power Pi saturation to P d mu I L over RT, which is equal to FIL Pi saturation T, that is the constant, to exponential then integration of Pi saturation to P VI L over RT dP. So if we combine these two equations, we can have this Fi for the liquid phase under the given pressure and temperature. This is equal to phi IV Pi T Pi e to the power integration Pi saturation to P VI L over RT dP. Now this VL of ith component is the molar volume of a pure liquid I, and at low pressure the fugacity coefficient and the exponential term, they are close to I. So we can represent close to 1, sorry. Then we can represent I, this is equal to Pi saturation. So by this way, because this is purely, you can say, sometimes referred as an ideal condition. So this is a very generic term. Now equilibrium conditions. The equilibrium conditions for low pressure vapor liquid equilibria, VLE, the equilibrium conditions can be written as Fi for the liquid phase to the fugacity at vapor phase, and this can be written as Xi gamma I Fi naught is equal to gamma I psi P, where Xi and gamma I, they are the liquid phase and vapor phase mole fraction of component I. Now the truncated virial equation, because virial equation of state is again very useful equation for determining the thermodynamic behavior of any component or any chemical component. So the truncated virial equation or ideal gas equation is often used as the equation of state. Now the latter case, all fugacity coefficients are 1, so the simplest form can be written as Xi gamma I Pi saturation is equal to gamma I P. Now in the case of low pressure liquid-liquid equilibrium, LLE, the equilibrium condition is given by Fi dash, Fi double dash, or Xi gamma I phi dash is equal to Xi gamma I Fi naught. That is the standard condition. Now the two liquid phases are indicated by a prime, that is this one, and double prime. For both liquid phases, the standard fugacity is chosen as the pure liquid component. In that case, it can be represented as Xi gamma I dash double prime is equal to Xi gamma I double prime. Now for calculation of high pressure vapor liquid equilibrium or liquid liquid equilibrium, an equation of state is always used for both phases. The equilibrium condition is used, which is usually given by Fi alpha is equal to Fi beta, or if we expand this thing to Xi psi I P alpha is equal to Xi psi I P beta, or Xi psi I alpha is equal to Xi psi I beta. Now low pressure vapor liquid equilibrium, since the polymer have no vapor pressure and as a consequence the vapor phase does not contain any kind of polymer. So the equilibrium conditions for low pressure vapor liquid equilibrium of polymer situation are only applicable to the solvent, because sometimes solvents are being added to the polymeric system to make more flexible, or the case where the weight fraction of polymer Wp is used as a composition variable. So in that case, P is equal to Xs gamma S P saturation, and that is P is equal to 1 minus Wp omega P saturation, where this omega is the weight fraction based on the activity coefficient of the solvent. Now, the relation between a mole fraction based activity coefficient and a weight fraction based activity coefficient omega s of a component I is given by this particular equation, that is gamma I over omega I, wi over xi, that is mi j is equal from 1 to summation n wj over mj, where wj is the weight fraction and mi is the molecular weight of component I. Now, P.J. Flory, along with this co-worker, they have described this thermodynamic behavior in a more elaborative way, and they adopted the liquid-liquid equilibrium. So, as per this P.J. Huggins theory of polymer solution, which is based on a rigid lattice model in which a polymer molecule is assumed to consist of R segments of a size of a solvent molecule. So, the Flory-Huggins expression for the Gibbs energy of mixing of Ns moles of solvent and Np moles of polymer, which is given as delta for the mixture of G RT is equal to Ns ln phi s plus Np ln phi p plus phi s phi p Ns plus R Np into xi. Now, first two terms in this particular equation of this particular representation, so called the combined entropy of mixing, and the third term in that particular approximation is for the enthalpy of mixing. In practice, xi, this is a Flory-Huggins interaction parameter, and which is used as an adjustable temperature dependent parameter, and phi s and phi p are the segment fractions of solvent and polymer respectively. So, we can represent these terms mathematically. Psi s is equal to ns plus r np, and this pi is equal to r np over ns plus r np. Now, according to the original Flory-Huggins theory, xi is given by, is proportional to 2 epsilon sp minus epsilon ss minus epsilon pp over t, where epsilon ss, pp and sp, they are the interaction energies between the two solvent molecules and two polymer segments and a solvent molecule and a polymer segment respectively. So, the expression for the mole fraction based activity coefficient of solvent and polymers, this can be written as ln gamma s is equal to ln 1 minus psi p plus 1 minus 1 upon r into psi p plus p square xi, or ln E is equal to ln 1 minus psi p r plus p, this is negative, r minus 1 minus psi p plus r 1 minus psi p r into xi, where r is approximated by the ratio of the molar volumes of pure liquid polymer and pure solvent. The activity coefficient of the solvent is strongly dependent on R for low values of R, but at high values of R and gamma S becomes practically independent of R. This implies the equilibrium pressure of low pressure vapor liquid equilibrium for polymer solvent system, which is hardly dependent on the molecular weight of the polymer. Now, in the original formulation of a Flory-Huggins theory, this delta G for the mixture increases with the decreasing temperature, which leads to the liquid-liquid phase split with an upper critical solution temperature. Now, per mole of lattice size, the entropy of mixing of the polymer solvent system is much less than for the solvent system. Because of this, polymer solvent system show a strong tendency to demix than solvent-solvent system. Now, here this particular figure shows the liquid-liquid equilibrium for polymer solvent system at a different polymer chain in length r, and this is calculated from the Flory-Huggins theory. You can see the changes. Now, this figure shows the influence of R on the location and the shape of the liquid two-phase region. With increase in R, you see that gradually we are increasing R, the two-phase region increases in size and becomes more asymmetric. The critical point, the temperature maximum of two-phase region shifts with increasing R to lower values of xi, higher temperature, and lower values of phi. Now, this at say R infinity, when we take this R infinity, the critical point found at the limiting value of xi half and t is equal to 0 and psi p is equal to 0. Now, this follows directly from the critical point condition where Gibbs free energy per mole, G is the Gibbs free energy per mole of lattice site. Now, this Gibbs energy relations, this can be written as del G over del psi p at constant pressure and temperature, del 2G over del psi p2 is equal to 0, which leads to this critical half 1 plus 1 square root of R and psi critical at given pressure is equal to 1 plus square root of R. Now, the theta temperature is usually represented as theta is the highest possible upper critical solution temperature within the framework of a Flory-Huggins theory. Many polymer solvent system, the temperature above this theta temperature show a second reason with the liquid-liquid immiscibility, which is characterized by the occurrence of lower critical solution temperature and sometimes which is referred as LCST. Now, this particular figure shows the liquid-liquid equilibrium at low temperature two-phase region with UCST at and a high temperature two-phase region with LCST. Now, this phenomena cannot be explained on the basis of the original Flory-Huggins theory. So, other co-workers, Delmas and Peterson, they calculated binary critical curves of polymer solvent system using the Flory equation of state. So, as per these authors, the reason for the occurrence of LCST is the large difference in the thermal expansion of pure liquid polymer and pure solvent, which leads to increasing difference in free volume with increasing temperature and LCST type liquid-liquid phase split at temperature below the critical point of the solvent. So, here you see this if the molecular weight of the polymer is increased, then UCST and LCST approaches to each other. Here you can see clearly. Now, another possibility that UCST and LCST never meets and each liquid-liquid region, this shows the difference of different theta temperature for R tends to infinity. Now, another type of LCST is connected to a specific interaction like hydrogen bonding. Now, this type of LCST temperature is found at temperature below the UCST. Here you see like this. Now, let us talk about the high pressure liquid-liquid and vapor-liquid equilibria system with separate low and high temperature region of demixing. The system in which the low and high temperature region of demixing have merged, showing a minimum cloud pressure, and system in which the low and high pressure temperature region of demixing have merged without the minimum cloud pressure. So, this figure shows the phase behavior of a binary polymer solution at constant composition in pressure versus temperature diagram. Now, in the case of say curve A, this curve, the mixture at a low temperature shows a liquid-liquid region characterized by UCST behavior, and a high temperature a liquid-liquid region characterized by LCST behavior. Now, the curve that separates the liquid-liquid region from one phase liquid region is often called a cloud point curve. The liquid-liquid vapor curve is found in many cases very close to vapor pressure curve of the pure solvent because of polymer concentration in the vapor phase and in the solvent rich liquid phase is low. Now, in this particular case, this again the PT diagram, a pressure minima. Now, pressure minima, at pressure below this minimum, the hourglass shaped two phase region they are formed. Now, in case of curve C, this curve, the cloud point curve is found at much higher pressure and no longer shows a minimum. Now, in going from a case A to case C, the mutual solubility of polymer and solvent decreases. So, dear friends, in this particular segment, we discussed about the different polymer solution behavior. Apart from this, we discussed different theories which are applicable for this phase behavior, and for your convenience we have enlisted couple of references which you can utilize as per the case needed. Thank you very much.